A hammer strikes glowing red metal in the dim light of a coastal forge, sending a spray of sparks across the dirt floor. The blacksmith is not forging a sword or a spearhead, but something far more vital to the survival of his people. He is shaping a small iron rivet. To the untrained eye, it is a simple fastener, but in the hands of a Viking shipbuilder, this small piece of iron is the key to a mechanical revolution. It is the component that will allow a wooden vessel to cross the treacherous North Atlantic and sail up shallow rivers where no other ocean-going ship dares to tread. The Viking Age was defined by maritime dominance, and that dominance was rooted in a specific construction style known as clinker building or lapstrake. Unlike the heavy Mediterranean ships of the era, which utilized a carvel construction, where planks were laid side by side, the Viking ships featured overlapping planks. This design created a hull that was remarkably thin and light, yet possessed a structural integrity that seemed to defy the laws of physics. The secret to holding these overlapping planks together under the immense pressure of the open sea was the iron rivet. The process of installing these rivets was a feat of manual precision. Once the oak planks were shaped and positioned, a hole was bored through the overlapping section. A red-hot iron nail was driven through the hole from the outside. On the inside of the hull, a small square iron plate called a rove was placed over the end of the nail. The shipbuilder would then use a hammer to flatten the protruding tip of the nail against the rove, creating a permanent pressurized seal. This clenching process ensured that the two planks became a single unified structure, but one that retained a crucial property: flexibility. In the brutal environment of the North Sea, waves can exert thousands of pounds of force against a ship's hull. A rigid ship, built with heavy internal framing, often risks snapping under this pressure. The Viking longship, however, functioned more like a living organism than a static object. Because the iron rivets allowed for a minute amount of movement between the overlapping planks, the entire hull could twist and flex with the rhythm of the waves. This flexibility acted as a shock absorber, preventing the wood from splintering and allowing the ship to ride the water rather than fighting against it. This mechanical advantage had profound strategic implications. Because the rivet-based construction required less heavy internal timber, the ships had an incredibly shallow draft. A Viking longship could carry 60 warriors and still float in just 3 feet of water. This allowed the Vikings to navigate deep inland via rivers, catching their enemies completely by surprise. They could beach their ships on any sandy shore without the need for a harbor, and then drag them across land if necessary. The iron rivet essentially turned a massive warship into a portable, versatile tool of expansion. The metallurgy of the rivets themselves was a testament to Viking resourcefulness. Most of the iron was harvested from bog ore found in the wetlands of Scandinavia. While this iron contained impurities, the process of fold welding and hand forging created a material that was resistant to the corrosive effects of salt water. Each rivet was a handmade product of intense labor. A single longship could require upwards of 7,000 rivets, representing a massive investment of time and resources. This was the high-tech industry of the 9th century. Beyond the rivets, the builders used a form of caulking that complemented the iron fasteners. They would twist animal hair, usually from sheep or cows, into a rope and soak it in pine tar. This rope was placed between the overlapping planks before the rivets were tightened. As the wood absorbed water and swelled, the tarred hair created a perfectly watertight seal that remained effective even as the ship flexed during a storm. The combination of iron, wood, and organic fiber created a composite hull that was centuries ahead of its time. The internal skeleton of the ship was also unique. Instead of being nailed to the ribs of the boat, the planks were often lashed to the frames using flexible roots or leather thongs. This further enhanced the ship's ability to bend without breaking. The iron rivets held the outer skin together, while the lashing connected the skin to the frame. It was a sophisticated dual system of fastening that maximized both strength and lightness. This is why a Viking ship could survive an Atlantic crossing that would have foundered much larger and more modern-looking vessels. As the centuries passed, the iron rivet became the foundation of a maritime empire that stretched from the shores of North America to the markets of Constantinople. The ability to move quickly across vast distances changed the course of European history. It facilitated trade, the exchange of cultures, and the spread of technology. And it all began in a small forge with the shaping of a simple iron nail. When we look at the remains of ships like the Oseberg or the Gokstad in modern museums, we see the weathered oak and the elegant curves of the prow. But if one looks closer, they will see the rows of rusted iron heads still biting into the wood. These are the silent witnesses to a golden age of engineering. They remind us that the greatest empires are often built not just by the strength of the arm, but by the genius of the fastener. The iron rivet was the small hero of the Viking Age, the mechanical bond that held a civilization together as it sailed into the unknown.